Today we'll be optimizing within a boundary. So this is completely different than the entire function. So back then you would look for possibly, I don't know, local maxes, local mins. But now you're looking for absolute maxes and absolute mins, not for within the entire system, but within a boundary. Therefore, you need to parameterize the boundary, which is the hardest part about this. But let me explain. If back in Calculus 1, you would have maybe some boundary. It would tell you, you would have a graph from 1 to, let's say, 5. And let's say the graph looks something like this, from 1 to 5. You'd be able to mark off the local max and local mins, but you would still need a test for the values along the ends or along the bounds of the function. And the reason why is because local maxes and mins don't mean absolute maxes and mins. This is what you're going to be doing today, but in multivariable calculus. So our first function will be x squared plus y squared minus 2x minus 4y. And this is our function. And our function is bounded by the points 0, 0, q, 0, 3, and point r, 3, 0. What does this look like? Well, this will just look like a triangle. This is point 0, 0, this is point 0, 3, and this is point 3, 0. And with along the bounds of this triangle, you're trying to find a local max or a local min by parameterizing your function. I'm just going to remove the other axes for space because we don't need those. So this is currently our function. This is currently our bounds, and we're trying to optimize within this shaded region of this triangle along the xy axis. So let's begin. Well, first thing we need to do is find local max and local mins. So let's find a local max within here by, or a local min, by deriving with respect to x and y. So our partial derivatives are 2y minus 4 and 2x is equal minus 2. Bah! So these both equal to 0. And the only values where these hold true is when x is equal to 1 and when y is equal to 2. So our first point is already found. P of 0, 1, 2. Is this point within this boundary? Well, this point 1, 2, yes it is. So if I were to draw out this point 1, 2, it'd be 1, like maybe here. But if you had a function for this boundary, that'd be better. But always make sure that the points you find, or the extreme of points you find, are within the boundary. Okay? So once we find this, what's next? Let's actually make this smaller so we get more space. And I'll move the graph. Once you find this, what do? Well, all you have to do is just plug in for the values of this point into the function. So f of 1, 2. So we plug in the values of 1, 2 into the function. So equal then sign. We get 1 squared plus 2 squared minus 2 minus 8. Notice how I just multiplied 2 by this. And this all equals to negative 5, I think, right? 5 minus 3, yeah, negative 5. So our first value is that we found, or our first possible absolute max, absolute min, is 1, 2 at negative 5. Okay, what's next? Well, we need to parameterize our boundary. How do you do that? Let's draw some arrows to represent these as functions. And this right here is along the x-axis, so y is equal to 0. That's our first parameter. And x is equal to 0 along this, not 5. X is equal to 0 along this parameter. What is this? Well, let's just use slope-intercept form, and then we get 3 minus x for our function along here. 3 minus x is equal to y, technically, for this parameter that's slanted. So what do? Well, you just have to plug in the values within your parameters into the main function. So our main function here is, let's use x equals 0 first. We'll keep y the same. So we got 0 squared plus y squared minus 0 minus 4y. Then our function is just equal to y squared minus 4y. And let's go ahead and just erase everything else. So now that we have a parameterized function here, what do? All you have to do is, now this is just a single variable calculus problem. So it's just a calc 1 problem. We just have to derive this, and we have to optimize along this parameter. Let's go find the derivative of this. So if we find the derivative of this, this turns into, let's write d over dy. The derivative of y squared is 2y, and the derivative of 4y is just 4. Now what is our value that makes this derivative equal to 0 because we're optimizing along this path? Well, y is equal to 2. Optimizes this. And keep in mind, we use the value of 0 for x and the value of 2 for y. So therefore, our point is 0, let's change the color, 0, 2 for here. And 0, 2 is along within our bounds. Now we have found the point 0, 2. Let's go 0, 2. If you've watched Darling in the Franxx, that's pretty funny. Okay, let's put this up here. Let's go save more space, and then let's go parameterize for y equals 0 this time. So we keep x the same, but we set y to 0 this time. And if you do all the simplification, you get just x squared minus 2x. Let's derive this x value, or this x function that's parameterized, and then we get 2x minus 2. Set this equal to 0. We're optimizing along here, and all we do is get x is equal to 1 for our parameter, or for our optimization along y equals 0, the parameter y equals 0. Well, what is this? Well, this is just along here, right about there. Yep. And that point is within our boundaries, so that makes sense to keep there. Now keep in mind, if you find some point that is outside of your boundary, you did something wrong, or that boundary doesn't count. Sometimes you will find a local max or local min outside of the boundary, so do not count that inside of your equations. But we found another point here, which is, this point would have been, so we use 0 for the y value, we got 1 for the x value. Let's go 1, 0. Okay, one last one. We need to parameterize with 3 minus x is equal to y. Start with this. Let's keep x the same, and we're parameterizing for y with respect to y, so we just substitute y with 3 minus x. What do you get? Well, you get x squared plus 3 minus x squared minus 2x minus 4, 3 minus x, and this is just more algebra, which is absolutely irritating, but if you expand all this, you get this. Plus x minus 2x minus 12 plus 4x. Let's go ahead and simplify all of this. These cancel out. What else cancel out? This turns into 2x squared. 2x squared minus 3. So this is our parameterized function. But then we need to find the derivative of this. Let's go ahead and derive this. Actually, you need to set this equal to 0. Oh, wait, no, we derive it first. So we derive this with respect to x because this is just our single variable here. If we derive this, we get 4x. Set this equal to 0, and x is simply equal to 0 here. If x is equal to 0, then what happens? Well, if x is equal to 0, then let's go underline this. If x is equal to 0 and y is equal to 3 minus x, that means y is equal to 3 minus 0, which means y is equal to 3. So our point for this is equal to 0 for the x value and 3 for the y value. Where's that on here? Simply up in the corner, 0, 3. And I think if I did this right, you would have gotten this corner as well. Oh, no, you would not have. Nope, you will not have. So these are 3 points right here. Correct? Actually, matter of fact, 4, counting the extrema point that we found. So if these are our points, what do we do with them? How will you be actually able to use these? Well, we already solved for our 1, 2 point, our extrema point, which is equal to -5. So let's keep that inside of a box. And then if we make a little chart here, let's get our xy values here and our z values here. Z, or same thing, our function value. So this is just z. If we plug in 0, 2, 1, 0, and 0, 3 here for xy values, what do we get for z? Well, let's be tedious. This is so tedious. Oh, I hate doing things like this. I just like the math part. I don't like the plugging in part. But if you plug everything in, you get, what is this? This is 0, so this is just 4. So 2 squared minus, this is just 0, 8. So you get negative 4 here. So our z value is -4 here. So for 1, 0, you get 1 plus 0 minus 2, which is equal to -1. So -1 is the z value here. We get 0 and 3, so the x values 0 out, so you get 3 here. 9 minus 12. Correct? 9 minus 12, yeah, this is equal to -3. So with this chart and with this -5 value, what are our absolute maxes and mins? Where absolute maxes and mins are -1 and -5. We actually already have that greened out. So our absolute max is at 0.10, which is the value of -1, and our absolute min is at 0.12, which is at -5. So what do we do? All we did was parameterize our boundary. We found absolute maxes and mins along the boundary by substituting our values into it, and we just derived it like a single, and we derived what we got after substituting into a single variable calculus problem. Like a single variable calculus problem. Parameterization is a pretty hefty one. And this one requires less calculus and more trig. We're going to be using the same problem for this because, I don't know, ChatGPT gave me this one. But this time our boundary is x squared plus y squared is less than or equal to 9. So the equal part matters because that means we are along a closed interval. So the boundary counts within our optimization problem. If we were to draw out this graph, it would look like, let me use perfect lines actually. If you were to draw out this graph, it would look like a circle. A circle with radius 3. Due to this function here, and the outside or the bounds of the circle would also count within our optimization problem. Okay, let's start. Well, how do you start this? First off, let's go find our local maxes and mins. In our previous problem, we found that 0.1, I think 1, 2 was it? Let's actually just redo it. X partial is this? Yeah, it's 1, 2. So our previous problem, we already found the local min of 0.12 equaling -5. So our function at 1, 2 is equal to -5. And let's change these colors to mark off that they are one of our potential absolute maxes and mins. Maybe I'll just leave this down here. And now we have to parameterize. Well, if you have a circle or anything cylindrical, whatever, you want to use polar coordinates. Yeah, maybe polar coordinates aren't that good, but they're very useful in cases like this. So in polar coordinates, x is equal to r of cosine, and y is equal to sine of cosine, sine of theta, r of cosine, sine of theta. R times sine, sorry. And for this, here's the thing though. We only are counting the boundary. So we don't want r to be a variable function or anything r to vary. We would just want r to equal 3 because we're trying to only look along the boundary. So in this, we want r equal to 3. Therefore, we only have just a single variable, theta. Once you do that, you can plug in our values of x and r and y. So we substitute it into our function. And then we get something that looks like this. I think it's 6 cosine theta minus 12 sine theta is equal to our function of theta now. If we simplify this further, we can actually factor out a 9 here to isolate cosine squared plus sine squared into its own parentheses. This just equals 1, so we can erase this. So it's 9 times 1, which is just 9. And then if we simplify everything, our function turns out to be this. Now all we have to do is derive this. If we derive this, we get 6. So if we find the derivative with respect to theta, this of f of theta of our function, this turns out to be 6 sine theta minus 12 cosine theta. Here's the thing though, we need to set this equal to 0 because we're optimizing. So you always want to set your derivatives equal to 0 when you're optimizing. Once this is equal to 0, we can move this 12 onto its own side. We can divide cosine on both sides. We can divide 6 on both sides to get our function simplified to equal tangent theta. We can isolate theta even further to get arctan of 2 is equal to theta. But what does this mean? Well, let's actually draw out this triangle. This is what I mean by trigonometry here. But I don't even know why that showed up. Ignore that. Usually I edit that out. Usually I edit it out if I accidentally press a key, but I don't care anymore. I'm not gonna lie. So our tangent here is equal to 2. Therefore, our ratio opposite over adjacent is 2 over 1. Because tangent of theta is equal to opposite over adjacent. And if our tangent is equal to 2, then our opposite is equal to 2 and our adjacent is equal to 1 with some ratio. Therefore, that means our hypotenuse is equal to square root of 5. So we can actually use this triangle because our angle is actually theta. Theta is this angle. What do I mean by that? What do I mean you can use this triangle? Well, let's erase everything first. Why do we want to use this triangle? Because it will make our life a heck of a lot easier when we are solving or plugging in for theta. We isolated theta, therefore we need to plug in theta into this function here so we can get our x and y values. Let's get our x and y values. X is equal to 3 cosine of arctan 2. How can you possibly solve for this? Well, we already figured out that our theta right here is equal to or related to this triangle here. So if arctan gives back a theta value, that theta value, or that angle, will be this guy right here. Therefore, our cosine will be the cosine of this theta value, which is simply just adjacent, which is 1 over hypotenuse, which is 5. And our cosine value turns out to be this. And if you just multiply it by 3, you get 3 over square root of 5. So this is our current x value. Let's figure out our y value. So our y value is sine of arc tan 2. Let's do the same thing. We just find the sine of this angle here. The sine of this angle is 2 over square root 5, which is simply equal to 6 over square root 5. Here's the strange thing about tangent values. In quadrant 1, the values of tangent are equal to quadrant 3. So, theta is an only arc tan of 2. But arctan of 2 plus 1 radian. And if you wanted to solve for that, this is simply just plus or minus for our current answers here. Now that we have our x and y values, let's go ahead and erase everything that we don't need. We should, well, first off, we should double check that we are within the boundaries. So, if we are within the boundaries? Well, plus or minus doesn't matter if you're squared or not. Whenever you square, you will always get a positive number. So, let's just put this into our boundary function to see if this is still less than or equal to 9. If we do all this, we get this is set equal to 9 over 5 plus 36 over 5, which is equal to 45 over 5. This is equal to 9. And 9 is certainly less than or equal to 9. So we are along the boundary, which is actually perfect. That means we've done everything right. So now that we have these points, what are the possible combinations of points? Well, the possible combinations of points are, let's see, 6 square root of 5. So just the positive values for this. We have 3 over square root of 5, negative 6 over square root of 5. We have negative 3 square root of 5, 6 square root of 5. And then we also have negative 3 square root of 5 and negative 6 square root of 5. And remember, we have to plug all of these values back into our function. But here's the thing about that. You don't need to plug all of these. You can just plug some of them. And the reason why is because of how, well, numbers work. Think about this. If your x and y values are both positive, what will happen? Well, this part of our function here is going to stay positive. But this part of our function is going to be negative. Because if x and y are positive, these minuses keep this part of the function negative. So that means this will be actually our lowest value. So this guy right here, I can already predict will be a min value. I don't know if it's absolute min yet until we plug it in. Wait, let me undo everything actually. And also, if you plug in all negative values, this will always be positive because of the square. But this right here will be both positive. These numbers will both be positive. If either x or either y were negative and the other one was positive, then, I don't know, this one would be positive and this one would be negative. This part of the function would be negative and this part of the function would be negative, and, well, it wouldn't be an absolute max or min. But, due to the property of numbers, we get this part, whole thing is negative, this whole thing is positive. I mean, this whole thing is positive, this whole thing is positive for this guy right here. And I can already assume this will be some form of max, or maybe even our absolute max. So we can actually erase the points that have only one of them that are negative, and we can actually just solve for these two guys. What did I do? So if we plug in the values here for x and y, we get 3 square root of 5 squared plus 6 square root of 5 squared minus 2 times 3 square root of 5 minus 6 times what is this? 6 square root of 5. Yeah, this is very, very annoying to do. But right here, we actually solve for this. This right here is basically our boundary function. So this part equals this part only just equals 9. This is 9 minus 6 square root of 5 minus 36 square root of 5. And we already have some constant, but let me pull out a calculator. Here, I have it here. And let's just find some decimal approximation of this. We can just use that. Minus 36 divided by square root of 5. And then this is equal to negative 9.78. So we'll use this number in order for our comparisons. At the end, let's actually just use green here. Square this. And then we have to plug in for this guy here. So for this, again, we have to do everything again. This is squared plus negative 6 over square root of 5 squared minus 2, technically plus 2, 3 over square root of 5 plus 4, because the negatives cancel out. That's why I'm putting plus. Negative here cancels out with the negative here. Plus 4, 6 square root of 5. Once you have all this, this part turns into 9 again. Then we get this guy. 4 times 6. Shoot, I used 6 here. I just noticed that this is not a 6. This is a 4. So I will change my answer. Previously, square root of 5. This is equal to. Hold up. Let me change my math. This is negative 4.42, and then the other guy, this guy, is 22.42. Therefore, once we have all of the z values, so all of these are z values, right, for a function, or a function value here, same thing. And so our absolute min is negative 5 because it's our lowest value. So our absolute min is at 0.12. Circle this. And our absolute max is at I'm not going to say all that. Again, I pressed the wrong button. This right here. Oh, that was a long one. But if you're willing to skip this last problem, I will not blame you because this is an extremely long video. And I have not made those electrical engineering videos, the circuit analysis, are way longer. I hate doing those. Nah, not hate. I kind of like making videos. It's kind of fun. If it's for you guys, which I don't know any of you guys, but hopefully I do. Yeah, if you guys have any comment, any requests for calculus videos specifically, or how to solve things, I can try to help you out. Or try to make a video on it, because teaching is quite fun. Q, R, S. That new alphabet is horrible, by the way. You gotta keep the LMNOP in. But these are our new bounds right here. What's our new bounds look like? Simply a square. So our new boundary looks like this. Just the square that's shaded in. So this is our new boundary. What do we do? Let's go find our local maxes and mins first. So our x partial is 2x and our y partial is negative 2y. Set these equal to 0, and again, it's just x equals 0, y equals 0. And at this point, 0, 0, what is our value for the function? Our value for the function is simply just 0. 0 squared minus 0 squared is just 0. So we have our first potential local max or local min, or absolute max, absolute min. I can leave that down there. And with this, what do we do? Well, right here is just another way to parameterize things. So we actually don't have to use functions this time. We can just set these equal to something. So this line up here is y is equal to 1. This line up here is y is equal to negative 1. This line is x equal to 1, and this line is x is equal to negative 1. So we have to plug all of these values into our function and then simplify it once again. So let's plug in, let's do y equals 1 first. Keep x the same. When y is equal to 1, you just get x squared minus 1. We want to derive this, so you want to derive this to get set it equal to 0, and our x is simply equal to 0. So our first point is, remember, we used 1 for our y value, so our first point is 0, 1. We used 1 for our y value, and we found 0 for our x value. Okay, let's parameterize the next thing. Let's do y equals negative 1. Same thing. You get still x squared minus 1. Derive this again. You get 2x equal to 0. X simply equals 0 again. But for this problem, our y value that we found, or that we used, was negative 1. Okay, let's parameterize with the x values now. So let's set x equal to 1. Let's keep y the same. If we can set x equal to 1, we get 1 minus y squared. Derive this. Then we get 1. Nope. What did I do? Don't zoom in. Okay. We get 1 minus 2. No, not 1 minus 2. We get negative 2y equals 0, and y is just equal to 0. So the values that we got for our x value is 1, and our y value is 0. Now let's use x of equals negative 1. So get still 1. And basically these are just the same steps. Let's underline everything. We get y equals 0 and x equal to negative 1. So our new extreme point is negative 1, 0. Okay, let's test all of these. Let's make our table here. X, y. We got 0, 1 here. Let's use a different color. We got 0, 1, 0, negative 1, 1, 0, and negative 1, 0 for x, y values. Holy shit, my hand is tired. Trust me, this pencil is not comfortable to write with. Oh my goodness. Oh, my hands are sweating too. But let's finish this problem. This one last problem of parameterization. So we plug in values of 0, 1 into this. We get 0 squared minus 1 squared, which is just equal to negative 1. Got negative 1's for our z value. How about for plug in 0, negative 1 into our function? We still get negative 1. And then if we keep doing this, we get 1, 0. get 1 minus 0. So 1 squared minus 0 squared, which is just equal to 1. If we do this again, we get negative 1, 0. Negative 1 squared is just still 1, so we always just make it positive on the inside. Just get 1. So these are values that we found. Now that we have our values that we can compare, right? So these are z values. Horrible box. These are z values, and this is our z value that we found for a local min. Which one's the lowest, which one's the highest? Well, negative 1 is obviously the lowest number, and 1's the lowest number. So this time, our local max or local min was not our absolute max, absolute min. We found our absolute maxes and absolute mins along the boundaries. And let's see, let's just write it down and let's end the video. So 0.0, so 0.01 and 0, negative 1 are, absolute mins, and 0.10 and negative 10 are absolute maxes. Finally, we're done with this. Oh man, my knuckles hurt. I'm gonna eat steak. I'm gonna eat a steak dinner today. I'm gonna eat a wonderful steak dinner today, prepped by my mom. So, if you have any questions, put it down in the comment section. Know this was a long video, but thanks for watching through if you did.